This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Well, we've been comparing things for a long, long time in science. And the main thing is we compare elements to assess their similarity. And we learned over time that we can associate sometimes similarity with function. And that comes back a long, long time, even before Charles Darwin was comparing big variations between birds that co-evolved. And on his trips to Galapagos Islands, for instance, he was taking a look at this species of finch, and they evolved similar beak variations. And the association between similarity and function is, this is basically to crush seeds, and they are indeed evolutionary related. So we learned over time to assess similarity and try to associate that with function. And what the availability of biological sequences that today we have allow us to compare organisms, but not only on an anatomical morphological way, but also in a molecular way, on a molecular level. And we do that so we can compare organisms in order, for instance, to find evolutionary relationships. And for instance, sequences can help us identify functionally conserved regions or sequences, for instance, what was conserved over evolution to get the same function. And with that, for instance, we can infer function. So let's say you have an organism, a model organism that has been extensively validated, and you have a new sequence that you have no idea what it does, but you know it's important for the organism. You can then ask the questions, do I have similar sequences in this database? And then infer function from this similarity. For instance, you can try to better understand the evolution of this sequence and evolution of this function, asking, can I find for my sequence other similar sequences in different organisms? Can I build a map of how this evolved over time, which will be an area called phylogeny? And in fact, we can do that these days, and for many protein sequences, we can reassemble their evolutionary history that traces back billions of years. So you can have a mammal sequence that can be traced back to bacteria, for instance. And this is a very, very powerful thing. You can build a really, really comprehensive tree of life that will allow you to better understand how these sequences and functions evolved over time. So that's a very important thing about sequence comparison, for instance, discovering functional and evolutionary relationships. And we assess this functional and evolutionary relationship basically trying to identify similar sequences. So alignments will allow you to identify similar sequences. And similar sequences might imply on a evolutionary relationship. So for instance, you get two organisms. Let's say I'm going to use a simple example, myoglobin, which is the protein that stores oxygen in our muscles. You get it from two different organisms or a series of organisms. We can try to infer evolutionary relationships by assessing their similarity. And usually when you have an evolutionary relationship, then you can infer a related function. So similar sequences could lead to an evolutionary relationship that can lead to a related function. And then it arises a very important concept here, which is homology. And I guess several of you have heard of it. Can anyone explain to me what's homology? Yeah? Minguyan? What's homology?
I guess it's from the same, the relatives. They're from the same origin.
The same ancestor, yeah. So basically, you say two sequences, two proteins, for instance, are homologs if they descended from a common ancestor, okay? And then you have a different concept, which is orthologs. What would be orthologs? Can anyone tell me what an ortholog is? So basically, homology will tell you, let's say, we get the myoglobin, for instance, example, which is a protein that will be common for frogs, humans, mouse. And the fact that we have a common ancestor that has that protein makes these homologs. Okay? And ortholog would be homologous sequences that appeared from a speciation event. For instance, we had a common ancestor between human and mouse, and because of that, they are orthologs. So we have a speciation event, and they have a common ancestor, and that was due to speciation. So sequences in separate species that derive from the same ancestor genes. And we have a different concept, which is paralog. Differently than paralog, we'll be looking for a duplication event within a single genome. For instance, a while ago, we had only an alpha chain myoglobin, and a gene duplication occurred, and then we now have a beta chain as well. So you have, within a given genome, different copies, and they could have diverged in terms of function. You can imagine that you have one protein that performs one specific function, and suddenly you have two copies of them. So one is free to evolve, for instance. So they could have diverged in terms of evolution. However, by definition, both orthologs and paralogs, they are homologs. So homolog is this overarching term to just say, oh, these sequences have a common ancestor. And there are really, really interesting things that we can do by identifying homologs, orthologs, and paralogs, and so forth. And there are various applications in bioinformatics for that. For instance, biological sequences, and that's the importance of sequence alignments. Biological sequences, regardless of their DNA, RNA, protein sequence, they're just data. They're just strings stored in a database. They're useless. They're not informative if they're just there, doing nothing. So what sequence alignment would do is basically the first step in many, many different analysis pipelines. Some of them we will cover on this subject to give them meaning. Okay? So it's a very important tool for instance, knowledge discovery. And sequence alignment is an integral part of different analysis pipeline. For instance, phylogeny tree is a very, very powerful tool. And without laws of generality, you can talk about two main tasks when you're talking about alignments. One of them is inference, when you actually have a new sequence and you want to discover what is likely the function of this sequence. You can look and search for homologs to try to identify functions that are already been experimentally tested and try to infer function from that similarity, that evolutionary relationship. You can also do identification and mapping, which is quite important, for instance, when you're assembling a genome. And you can do really, really interesting things with a tool that is relatively simple and really elegant. Just to give you a really quick example, this is not self-promotion, but it is. Just a paper I was working on that was recently accepted to Cell Host and Microbe. We were interested in understanding the evolution of one particular protein that is very only common to Leishmania parasites. For those that don't know, Leishmania causes leishmaniosis, so it's a parasite very common in South America and other parts of the globe. And what we were looking at, this specific protein called MKT, they are really important for infectivity in the mammalian host. So how Leishmania works is it has one of the hosts is the mosquito, then the mosquito bites the human, and then it's transmitted to the human. And these proteins called MPTs, they're really important for infectivity in the mammalian hosts. And Leishmania parasites, but only Leishmania parasites, have 7 copies of them. And we were trying to identify where does this came from, because these proteins were really, really important for carbohydrate biosynthesis in Leishmania, so they were really interesting new protein targets. And what we were able to do, just doing sequence alignments and trying to reconstruct based on this sequence, finding homologs, where does this function come from? We were able to reconstruct the evolutionary history of these proteins, tracing back to bacteria. And we came up with the hypothesis that they were actually originally transferred via horizontal transfer from gram-positive bacteria. And the neat thing is, actually they were commonly found in the mosquito gut microbiota, so it makes sense evolutionarily. And this probably allowed them to colonize a new host, the human. And it also it's a very, very different protein family, and actually it's a new family of enzymes called glycosyltransferases. So it's actually annotated differently for anything else. And this is just a quick example of what we can do, but One of the main areas of uses of sequence alignment is definitely phylogeny. It's something we'll cover next week. And the main question on phylogeny is, given a set of related homolog sequences, we'll try to infer evolutionary relationships between them to try to build a tree view of how these sequences evolve. We can also use sequence alignments for representing function. So given a newly identified sequence, we will be interesting, for instance, to find regions which are similar to proteins with known function, which have been validated before, to try to infer its structure and function, or maybe annotate its function. So come up with a hypothesis. So you have something that is very similar, that I know the function, can I try to understand what this is doing? And in terms of conservation, so given a set of homologous sequences, try to find conserved regions, and that's applicable for both DNA and RNA. I might be interested, for instance, in regions of this sequence that have been conserved over evolution more than the rest. First, in DNA, we might be interested in regulatory elements. In proteins, very important binding sites or catalytic active residues and so on. And alignments, they also have a variety of other uses. As I mentioned, you might be interested in database searching. So given a novel query sequence, how can I then find similar sequences in really, really large database? And we're talking here terabyte scale, petabyte scale. Therefore, we need a very, very quick approach for this. And for instance, will allow us to ask what species of bacteria are in my sample, for instance. And this, as I mentioned, is very important for de novo sequence assembly. Let's say you have to reconstruct a single sequence from really, really tiny sequence reads. And I'll basically try to align them together to reconstruct this original sequence. And it's also important for read mapping, which will be given us reference sequence. How can I align this small bits to the reference? And also infer variants from it. And just to start off with a very easy approach to how to compare sequences, one way to compare sequence will be with the concept of edit distance. So the edit distance of a string, let's consider our sequence A string, will be the minimum number of edits needed to convert one string to another. And of course, it depends on how kind of edits you can do and operations. Let's say we only consider substitutions. If we only consider substitutions, that means we only assessing for, to start off with, sequences of same length, okay? And this is originally called Hamming distance. So Hamming distance is the minimum number of edits, the substitutions, in a way that I can morph one word to another. Same number of characters, okay? For instance, what's the Hamming distance between the words push and the word push? Which, by the way, it's po in Portuguese. So they sound the same. So you can imagine, if you see me opening a glass door and actually trying to do this, that because I read push, my brain hears push, and I think it's po in Portuguese. It's quite confusing. Yeah, but what would be the Hamming distance? So the minimum number of edits, I'm only doing substitutions to convert push to push. 2. I basically need to do one substitution here, one substitution here. What if we not only consider substitutions, instead we'll consider substitutions and one letter insertions or deletions that we're going to call from now on indels, okay? Now we are able to consider sequence of different lengths. If I can delete or add characters, I can consider sequence of different lengths, which is something quite important. And there is a simple algorithm to calculate that. So the minimum cost of single letter indels and substitutions to convert one string to the other, which is the Levenshtein distance, okay? And in order to do so, since we're talking about cost, we need to define what's cost. If you look at only substitution, let's say I just need to minimize the number of substitutions, but it will be interesting to treat indels and substitutions differently. For instance, we need to penalize mismatches and indels, okay? So I can have matches or either mismatches or indels. And let's say we penalize it with a +1.
What are indels?
Insertions or deletions. Okay? And let's say we penalize them with a +1. And let's say we don't penalize matches. So matches would be 0, indels would be 1. And let's try to convert Sunday to Tuesday. How many operations, or how would be the cost, considering this scoring system, to convert Sunday to Tuesday? What would be the minimum? Yeah? 2, 3? Anyone? Where's Grace? No. That's fine. For instance,
So what should be the reference? It really depends on the reference.
you will have, the first thing is you would have multiple options, right? How many different alignments I could have. So how many different editions I could make to go from Sunday to Tuesday is a huge number of possible ones, right? I'm interested in one of them that has the minimum cost. We could therefore have 2 different sets of editions that lead to the same cost. It doesn't matter. I'm just interested in the minimum one. Okay? Let's try to do this, for instance. First thing you notice, we have a common day here and here. We have a U here, a U here. So let's try to convert Sunday to Tuesday. We do a mismatch, S to T. Then we have a match, U with U. Then we could have, for instance, a mismatch, N to E. And Tuesday has 1 more letter, so we have to have a gap or indel, which is S. And then we have 1, 2, 3 matches. So our options are really, I have a mismatch, or I have a match, or I need to do an insertion or deletion. And a quick and simple Python function to calculate the Levenshtein distance will look like this. So Levenshtein distance of 2 strings A and B will have basically to evaluate the minimum value, so I want the minimum cost, between insertion or deletion in one of them, in A, let's say, in B, or calculating the mismatch cost. So we have these 3 components here. And the mismatch cost will probably be, will actually be 1 if it's a real mismatch, or 0 if it's a match. So we are not penalizing matches, but we penalize insertions and deletions and mismatches. Okay? And this is a very simple function, but what's the time complexity of this? This will actually give us the optimal. And the number of potential alignments that it's going to access is quite big. So for each step, for each character, it's going to generate 3 calls for the Levenshtein. And each of them will generate 3 more. So you have 3, it's like a tree. You have 1 here, then 3, then 9, then 27, then 81, and it goes on and on. So what's the time complexity of that in terms of the number of calls for that function? As you could notice, this is a recursive function definition. What's the time complexity for that? For a sequence of size n, for each character, I'll call this function 3 times, and then 3 times again on the tree. And we'll have a very untractable complexity. This is not going to work for large sequences, or if you need to do this multiple times. Okay? So when we're talking about pairwise sequence alignment, so I have one sequence and the other, and I want to compare them. We have usually 3, without loss of generality, 3 major approaches. The first one is the global alignment. So in global alignments, we are interested. Yeah. Anyone else? Oh, sorry.
For that indel fields, do we consider like conversion Sunday to Tuesday? Do we consider the mismatch first and match and then indel?
Oh, that's on the algorithm. So you could have multiple options. Probably not on this very simple example, but you could have multiple orders that will lead to the same results. It doesn't matter. You're trying to find the minimum cost, right? So there isn't a rule what you do first, as I'm going to show you in the actual algorithm that we're going to use. Okay? And in terms of the... And in terms of the number of calls, this is exhaustive. this will try every single combination. And this is very slow because you're accessing and evaluating things multiple times, as we're going to discuss. But there is no, the algorithm we're going to discuss, it doesn't say evaluate this first and that first, okay? So in terms of pairwise sequence alignments, I have two sequences. I want to assess similarity, for instance. We can do it globally. So we're basically interested in the best alignment over the entire length of two sequences. And this is suitable when you expect that across the whole sequence length, you have a certain level of similarity, okay? And the sequences have similar lengths. If you try to compare 100 residue protein with a 3,000 residue protein using a global alignment, you won't be able to have a good score because of the number of gaps you need to insert, just because the sequence lengths are too different, okay? And we're going to discuss today the optimal way to do this, which is the Needle-Whoosh algorithm, which uses an approach called dynamic programming to solve this in a more efficient way, okay? In terms of local alignment, the main goal here is to identify regions of similarity. And this is more appropriate when, one, we have substantially different sequence lengths, and the overall similarity it could be quite low. And this is applicable, for instance, when you have a protein domain that is conserved, but overall the protein sequence is not that conserved. And we do that using the Smith-Waterman algorithm, which we'll also discuss today, which is a modification of the Needle-Whoosh, which is also based in dynamic programming. How many of you have heard of dynamic programming before? Okay, not too bad. And we also have heuristics for local alignment. One of them is the famous BLAST, basic local alignment search tool, which we'll discuss briefly as well. And the third alternative is a semi-global alignment. And this is applicable, for instance, when you have a really, really long reference and you have a really short query, okay? And this is, of course, applicable for read mapping, when you want to, let's say, map your reads to a reference genome. And in terms of global alignment, then we're going to dive into the Needle-Whoosh algorithm. So basically, global sequence alignment, we're going to try to do this. So superpose the two sequences in a way that we are minimizing the score. And for instance, in this case, we have this nucleotide sequence and this nucleotide sequence. And this is the best alignment for them. It doesn't mean it's the only single best alignment. We could have multiple alignments with the same score for this one, especially because it's a very small example. And what we see here, we see introduction of gaps, 3 of them. We have 5 matches and 1 mismatch, okay? However, we need to deal with a really, really large number of potential global sequence alignments, and we're basically interested in what's the best one given a scoring system. So how I give points to matches and how I deduct points for different types of mismatches and gaps or indels. And let's say that our score is the following. Let's say we give 1 point for matches, we remove 1 point for mismatches, and 1 point for insertions, deletions, which would look like this, a gap in the alignment, okay? And let's say to score this alignment here, we would have 5 matches minus 1 match minus 3. So the overall score for this alignment would be 1. And in this case, is the optimal. And we know that our recursive Levenshtein algorithm, which would find the optimal, the cost is exponential. So it's not feasible in the real world. And the question now is, how do we go from just a simple editing distance algorithm for something that will be able to cope with the amount of data that is available in bioinformatics and biological databases? So how to reduce the massive number of possibilities that Levenshtein tries?
Why you have one mismatch of
I'm sorry? We have 1 mismatch. Yeah? Which is this one, C and G. And we have, let's go one by one. So C and a C, that's a match. A and nothing, that's an insertion deletion, indel. Then we have a match, insertion deletion. Then we have a mismatch. Match, match, indel, and match. Okay, is that clear? And one thing what we would like to do is not only reducing the cost of this algorithm, but also making sure we still guarantee that the best solution will be found. And for that, we have a 50-year-old algorithm called Needleman-Wunsch. It's a very, very elegant algorithm. So the basic idea of Needleman-Wunsch is to build up optimal alignments using optimal alignments that I know for smaller subsequences. Okay? And this uses dynamic programming. Dynamic programming basically is a divide and conquer strategy and is adequate for problems with optimal substructure. This is saying that, let's say I have a given sequence, and if I know the alignment, the optimal alignment of this region, this will be part of the global alignment as well. A different way to understand optimal substructure would be, let's say, in the shortest path calculation algorithm. So let's say we have a network, road network of Australia, where the cities are the nodes and they are connected by roads. And we want to find the shortest path between A to B, let's say Melbourne to Perth. And what optimal substructure will say is, let's say we know the optimal response for the Perth to Melbourne route. And let's say we have an intermediary town that we need to go by that is, I don't know, geography. Any cities between Melbourne and Perth? And Adelaide, for instance. So let's say your shortest path between Melbourne and Perth needs to go through Adelaide. So optimal substructure will say that the shortest path from Perth and Adelaide to Melbourne will also be also be optimal. So if you have an optimal that goes from Perth to Melbourne, Perth to Adelaide will be optimal as well. Okay? So in this way, you can solve the big problem starting with the smaller ones. And in dynamic programming, that has to do with basically making sure you don't compute the same thing over and over again. So you keep track of what you're doing using a matrix. So dynamic programming is a pretty name for filling up a table. Okay? It's a very elegant strategy. And Needleman-Wunsch will basically do is, we have basically 3 steps. So we need to create an alignment path matrix. Okay? Everybody knows what a matrix is? So it's a 2D vector, so it's a common data structure that it's indexed by column and row. So for Needleman-Wunsch, we'll need an alignment path matrix and a backtrack matrix. Let's call the alignment path matrix S, indexed by column and row. In the second step, we'll populate this table following a few rules, and we'll do a stepwise calculation of scores as we go along. So we'll try to align one by one, and we'll populate this table. And on step 3, we'll do the backtracking to actually get the actual alignment. Okay? So on step 1, we will have the creation of the alignment path matrix, which would look like this. So you basically have 2 sequences. This is an amino acid sequence, VGSCY, and you have the other one, VESLCY. You basically put one as columns, the other one as rows. And this is my alignment path matrix, Sij, and it has I columns, j lines, which are the sizes of the 2 sequences, which could be different. In this case, it's 5 and 6. And basically, you can do 2 types of moves to populate this table. Apologize. You can do horizontal and vertical moves. Let's say if you go from here to here, or from here to here, which are equivalent to inserting gaps or indels. And the thing we're going to do here is basically initialize all the gap penalties. Let's say we have an arbitrary number, -8. So we start initializing these gaps with -8, -16, 24, and so forth for both of them. Okay? And we can have diagonal moves. Diagonal moves will mean either a match or a mismatch. And the final alignment would be a path from the top left corner to the bottom right corner. And on the bottom right corner, we'll have the optimal score of this alignment. Okay? And what we do, we start populating this. So let's say if we don't align them at all, so basically we'll have the first sequence, all gaps, then the second sequence, all gaps. The path on the alignment matrix will be something like this. Gaps, and then gaps. Is that okay? So that's the worst possible thing you can do. So you just penalty plus penalty plus penalty, and that means I'm just inserting gaps. Okay? That's one way to interpret this. We're trying to find a path here that optimizes the final score. And the way we populate this, which is the step 2, you need to populate the table calculating Sij. And you basically need to know 3 things to calculate Sij, which is the value to transition diagonally, which is a match either or a mismatch, which is this thing here. And let's say Mij is the match or mismatch score. And you also need the gap penalty. So you can go from here to here and from here to here. In this case, we're using gap penalties of -8. And Sij will be then the maximum value. We're trying to maximize the scores here. And this is that. No. Maximize the actual values here. Let me just, yep. Maximize one of these 3 values. So we want the maximum possible score. Okay? So we're going to choose between the diagonal, left to right, on top to bottom. And in this case, let's say we have the following options. So we have a match option. Let's just consider that changing from one, the match between 2 valence residues is 4. So we have an option to transition from diagonal, so it will be 4, and insertions, deletions would be -8 and -8, and we choose the maximum, which would be 4. So we populate this table here, so it's 4.
Are 4 and -8 just numbers you've chosen, or is it always using this number?
We are going to discuss on Friday what's the effect of choosing these numbers. So as you can imagine, if I change them, the alignment's going to change. And there has been a lot of effort, a lot of research on how do I define a scoring system. And what people have done, come up with are scoring matrices, which you have scoring matrices for nucleotides, scoring matrices for proteins, and they will be different according to the question you're asking, basically. But let's say for now these are arbitrary, okay? But bear in mind they will affect the final alignment, of course, since I'm trying to optimize the value of the scoring of the alignment. And then I'll try to populate the next one and moving on. So for the next one, which would be this cell here, I have 3 possible options. Left to right is always a -8 gap value. Top to bottom also -8. And let's say here we have a mismatch. Is V from D. And let's say the mismatch from V to D is -2. And then I can choose between 8 minus 8, which is -4, 8 plus -2, which is -10, or -24. And I choose the maximum value, which would be -4. Okay? And I keep doing that for the whole matrix until I have completely populated the table. Okay? Keeping track of the directions I've chosen. So I not only need the numbers, but I also need the arrow direction. Okay? And basically, once I've done that, on the bottom right corner, we have the optimal global alignment score, which in this case is 23, considering these values we used for matches, mismatches, and gaps. Okay? And the step 3, finally, is recovering the actual alignment, which is done via backtracking. So if we take a look at the bottom right path, we'll try to understand where and how we achieve this alignment, with basically following the directions of the arrows. So the first one is a diagonal. In this case, it's a match. Then we have another match. Then we have a vertical one, which is a gap insertion, and then 2 more matches or mismatches. Okay? And with that, we can reconstruct the alignment. So we always start from the lower right, and we build our work up following the arrows and see how we get there. So basically, we need those two matrices, one to keep the scores and the other one to keep track of the arrows. And we end up with this alignment, which is the optimal global alignment for these two sequences. Okay? Sorry. Which will have a score of 33. So interpreting these arrows would be, here I have a match, yeah. Here I have another match, so I'm going diagonally. Then I have an indel, a gap, which is here. Then I have another match. In this case, I have a mismatch. But it's also matches and mismatches are in the diagonal. And finally, another match. But if you think about the scoring system, D and E is a mismatch. But why D and E was actually chosen instead of a gap? Because in this case, in this scoring system that we're going to discuss, this was considered a small change. So anyone knows what a D and an E in terms of a protein code is? These are residue coding values. Aspartic acid, very good. It's a D. And E? It's an acid as well. Glutamic acid. So they're very, very similar. Both of them are negatively charged. The only difference is E is slightly longer in terms of the side chain. So they are similar residues that can perform similar functions. It's called a conserved mutation from one to the other. And that's probably the reason why we chose a mismatch and not a gap. Okay? And there we have our global alignment.
The gap vector should be increasing.
What, sorry?
The gap vector, is it always increasing? Like you started with -8 and -16?
It's always increasing because we are considering a path. So an alignment is a path in this matrix. You're starting from top left to bottom right. Okay? Why do I have cumulative numbers here? So let's say, just consider this bit here. Okay? So let's say this is just the beginning of our sequence, and we have a long sequence here. But none of them match with the other one. So we would have basically 5 consecutive gaps. And each penalty for a gap is 8, therefore we keep increasing them. So if you don't align them at all, so you have 5 gaps plus 6 gaps, then you continue adding 56, 64, 72, 80, and so on and so forth. That's why it's cumulative, because it's like you're following this path. Does make sense? Yeah? So what will be then the time and space complexity of a general dynamic programming? Actually, it's applicable to all of them. So what's the time complexity? And in this case, which is the same as the space complexity in terms of the big O notation for Needleman-Wunsch? ON squared. What if your sequences have different sizes? Very, very different sizes? N times M. Yeah, which it could be N squared if you consider the largest one. It's correct. So it's basically filling up a table. It's the number of elements in the table, which you can say, yeah, it's N squared, it's a quadratic. Okay? And that's valid for in terms of in time and space as well. And of course, this will be affected by the scoring matrix. So this is a very, very important matter, choosing the right scoring matrix where you will say how much you're going to penalize the gap and the mismatches and how many points you're going to give to the matches as well. It's something we're going to discuss on Friday. And of course, as I mentioned, different scoring systems have been proposed. Mainly, we need to understand that some mutations are conservative. For instance, you can change residues that have more or less the same size, the same physical chemical properties. That's valid for nucleotides as well. And this, once we have an alignment, then we have 2 more concepts that are quite important, which is similarity and identity. So identity will tell how much of that sequence is actually identical. So how many actual matches we have. And let's say in here we have 4 of them. For a sequence of size 6, we have 67% identity. And similarity could be something, how similar they are. We'll consider mismatches as well, so it would be something around 5 out of 6, 83% similar. So similarity and identity are quantitative metrics. Not to confuse with homology. So when you say two proteins are homologs, either they are homologs or not. You don't say they are 75% homologs, okay? But you can say they are 75% similar or identical, okay? And then we go to the next part, which is local alignments. And for local alignments, we'll focus on the Smith-Waterman algorithm. So differences between global and local. On global, we're basically looking, well, your final alignment will have the same size up and down, and we're therefore looking for a global similarity between two sequences, and we expect that similarity would be consistent throughout, okay? While local alignments, we want to identify the most similar subregion. We don't care if we have this. We have different lengths, or if only one portion is conserved. That's the main goal for local alignment. And global alignment is a very good method, of course, when the whole sequence is expected to be related. And it's basically, when you look at that path matrix, it's going to find the best scoring path between the top left and the bottom right corners. While local alignment is very good to identify local regions of similarity, and it will try to identify the longest path among the arbitrary sets of vertices on that same edit graph. So it's a derivation from Needham-Wunsch. And this is very important because often we expect the only part of the sequence it's going to be related. For instance, we can have DNA sequences that often have highly conserved regions, especially for fundamental biological process that will be more conserved than the rest, and that's true for protein domains as well. But you can consider as a biological module that can be, for instance, reused by different proteins. So you're looking at a very specific region. So you need to look to align globally. And you also have proteins that contain multiple domains. So basically, Smith-Waterman will also use programming, dynamic programming to solve the alignment problem. And we'll also use two alignment matrices, the alignment scoring matrix and the traceback or backtrack matrix. And it basically has two main changes from the global alignment algorithm. One of them is we're going to this time initialize gaps with 0 penalty. That's a way basically to allow alignments of sequences of different sizes. So the first line, first column will be set to 0. Okay? And the other thing is that the traceback for finding the optimal alignment won't start on the bottom right corner. We actually are going to start from the largest score in the matrix, which will then render our best local alignment. And that's pretty much it. And then we'll have, additionally, a stopping criterion for the algorithm is when the value of the matrix is negative, we'll set it to 0. And this has the effect of terminating the alignment. Okay? So we'll end up with this. So the way we are going to calculate each of the cell of the matrix will be we'll have a mismatch or a match. We'll open a gap from one or the other sequences, or we stop. Okay? And we then fill up the matrix in the same fashion, one by one, stepwise. Okay? And for example, we'll try to find the local best alignment for the words happily and applying. And looking at this, so we already calculated all the scores here. We'll start with the largest score, which is 4. And we're going to trace back what's the path that got us to 4, which is basically a match or a mismatch, another match or mismatch, and then we have a gap, and then 2 matches or mismatches. Let's see if that's the case. Yep, that's it. So we start with 2 matches. 2 matches, Y with Y, L with L. Then we have a gap on one of them, and then 3 more matches. But bearing in mind we didn't align the whole of the sequences. We went for a local alignment. And this renders the optimal alignment score of 4. Okay? What's the time and space complexity of this algorithm?
Sorry, like the previous one, is that supposed to be the maximum, not minimum?
Oh, yes, sorry, I forgot to mention this. Yeah, very well spotted. Since we are starting the gap penalties with 0, in this case, we're trying to minimize the score, not maximize. We're trying to minimize this value here, not maximize. Yeah?
This exact example, I think, is it from Claire? I don't know. But
Yeah.
it was used in last semester's genomics.
Uh-huh. Yep, this one, yeah.
And it was exactly the same example, and it was a max in there.
It was a max?
Yeah, the code itself, it was in max.
Okay. Okay, is this? I'll double check and upload back again on the elements. I'll check that for you.
Because if you're trying to find the
Yeah, it makes sense. It makes sense. The match is positive. Yeah, it makes sense. Sorry about that. They're mistaken. That's definitely a max. Thank you. Yeah, in this case, the optimal alignment score is 4. And in terms of time, space, and space complexity for this problem, it will be the same as the previous one, right? So we're basically filling up a table with n columns and m rows. So we also have a quadratic algorithm there. And with the difference that we have an extra step to find the best score within the matrix. So we need to search the matrix. So we do basically this twice, which doesn't change the big O notation. Is that clear? That if I multiply this by 2, it's still quadratic. Yeah? Okay. And yeah, that's a very, very interesting algorithm with a decent time complexity. But would it scale when you're considering hundreds of millions of sequences? So the problem is, for the scale of the problem, quadratic is not good enough for most of the time. When you're trying to query hundreds or thousands of sequences towards a really, really large database, is just not going to run in time, okay? And we need a faster solution. And for that, we have heuristics, and we have BLAST. BLAST is probably one of the most famous tools in bioinformatics. It's the basic local alignment search tool. And what it tries to do, of course, is finding regions of local similarity between sequences. A very clever heuristics that works not only for proteins, but nucleotides as well. And he also calculates something very clever called the statistical significance of the matches, which is really helpful to better understand whether what you found was found by chance or whether it has actually a biological relevance to it. The main 2 papers for BLAST are amongst the most cited papers in biological sciences or ever. So they accumulated over 150,000 citations over the years. And they come in 2 different versions, without and with gaps. And this is a 30-year-old algorithm now, which is still extremely important and used. And just for you guys to have a quick flavor of what BLAST does, is a bit more complicated than the other 2. But what BLAST is going to do is, the main idea is I'm going to pre-index a database of sequences I have with words of length W. Okay, I'm going to chop up all the sequences in the databases of a given size. Let's say usually the default for BLAST proteins are 3 and DNA 11. So we'll have a sliding window. So 1 by 1. So the first 3, let's say the alphabet. For proteins will be A, B, C, then B, C, D, then D, E, F, and so on and so forth. So we have K minus 3 words in a given sentence. Okay? So the thing I'm going to do is, I know I have a really, really big database, and I'm going to index the sequences saying, okay, the sequence has these words, the sequence has this set of words, and then I'm constructing a dictionary that will be quick to access and index. And basically, I'm going to do that with my query as well. So I'm going to chop up my query into small words and create a word set, and then I'm going to query my large database to try to identify where those small words match. Okay? But I'm not only interested in exact matches. So I'm going to try, this is from my, let's say, my query sequence, and I have a large data set here. I'm going to check where each of these small words match with a minimum score of t. This comes to do with the score matrix as well. So the score matrix will affect this as well. So let's say we only need really, really high scores for that. And then what we're going to do is try to match the words from the query and the database, considering that value. And we'll initiate and extend the local alignment from these small seeds. And we'll then try to find a local optimal ungapped alignment, which they call also a HSP, high scoring pair. So basically, I'll try to really quick just match those small words that are simple and try to extend that pattern for all of these sequences. And then what BLAST will do is report either a given number of hits or all the hits that are lowered with an E value, expected value, lower than E. And this is a very fast heuristic, so of course it's less sensitive than the full local alignments. And also have a running time in the worst case is the same, however it's considerably faster than Smith-Waterman. And one important thing that BLAST outputs are the way it scores the alignments, and you have the alignment significance, which is the E-value, which can be interpreted as the number of unrelated sequences that are expected to yield the same or higher score by chance. So the lower the value, the more relevant the hit is. And this decreases exponentially with the score assigned to a match between two proteins. The smaller, the better, even though there are default values for BLAST. For instance, e to the minus 4 for protein searches, e to the minus 10 for nucleotides, is a very interesting and easy way to determine a significance thresholds when you're actually reporting your results. So it's basically what's the chance of finding that alignment by chance, or rather that it's a really rare event, and then you can infer that there is a biological meaning behind it. And of course, these E values will vary based on the database you're searching and the query you're using, of course. And that's it for today. Any questions? Thank you.
First question.
Yeah.
This direction are all the matches.
Yeah.
Right, but the score they are different from here and here.
So basically accumulation of scores. Sorry.
I have a thing.
Yeah. For instance, what happens here? You're summing them up.
For
So you have
example,
0 plus 4.
The score of match is positive 4.
Yeah, positive 4, and then
But it comes to here, the score of a match becomes positive 10.
oh yeah, because the thing is, I probably should have explained that the scoring matrix is different. So for instance, we have a score for VD, and we have a different score for different pair. We have a scoring matrix. That's what we're going to discuss next time.
Score of match, I have to carry a score matrix first.
Yeah, that's the most important thing actually, is defining a proper scoring matrix. For instance, to understand that D to an E, that's not a problem. But if you have a D to a Y or D to a K, that should be penalized because they are completely different residues. Okay?
And for this case, you have assumed that the sliding window length is like 11 for DNA.
Yeah, that's the default input parameter for BLAST.
Is this based on some logical?
No, that's heuristics. So they actually try different things compared with, because the thing you can do is you have the optimal algorithm, so you can actually tune this based on the optimal and how close you are to the optimal. So this is their way to tune
How
things.
can I know that the optimal solution is in the length of like 11 or some?
It could change slightly. Well, they did a lot of experiments. You can take a look at their paper. They show that 3 and 11 are good starting points. But one thing about alignment is you're going to end up actually looking at